Hey there, welcome to Take Break. Get ready for a mind-blowing math adventure that'll twist your brain. Imagine taking a solid ball and making an exact copy of it out of thin air. Sounds impossible, right? It feels like something straight out of a sci-fi novel, yet the proof lives in pure mathematics. In the early 20th century, mathematicians Stefan Banach and Alfred Tarski stumbled upon a paradox that would shock the world. They showed that a perfect sphere can be dissected into a handful of bizarre pieces, each wildly scattered. And those strange fragments can be rearranged, without stretching or adding material, to form not one, but two identical spheres. Here's the trick. We're not cloning anything, just playing clever geometry. By cutting the sphere into oddly shaped pieces, we can shuffle them around like a puzzle. But there's a catch. These pieces are anything but ordinary. They're not the smooth chunks you'd expect, but bizarre, almost ghost-like fragments. You can't pick them up or feel them. They're not solid at all. Imagine trying to hold a shape that slips through your fingers like vapor. Each piece is scattered to infinity, like dust motes drifting in that single beam of light. Together they hint at the original sphere, but individually they're just specks. Picture a cake sliced into crumbs that you can't actually see. Tiny, invisible pieces floating around the table. Now, with a flick of mathematical magic, those invisible crumbs snap back together, forming a whole cake again, just as the sphere doubles itself. Now we bring in the secret sauce, the axiom of choice. It's the rule that lets mathematicians reach into infinite collections and pluck a single element from each, no matter how wild the set. Think of it as a magical picking hand for the infinite. With that axiom, you can choose one point out of every conceivable group, even if the groups are infinite. No algorithm, no step-by-step recipe, just the assurance that a choice exists. It's like saying, pick a grain of sand from each beach worldwide. And it works for infinite collections, too. You don't need a computer or a stepwise method. The axiom simply guarantees a selection exists, even when there are infinitely many choices to make. It's a kind of mathematical trust in the impossible. Armed with those arbitrary picks, we can carve the sphere into wildly exotic pieces, sets that are so scattered they look like dust, not solid chunks. These pieces are defined purely by the choices we made, not by any physical cut you could make with a knife. Why does this feel so wrong? Our brains expect volume to behave nicely. Cut something, you can't get more out than you started with. But these strange sets ignore the usual rules, so our intuition hits a wall. The kicker is that volume simply doesn't apply to those crazy sets. Since they're non-measurable, they have no well-defined size, so doubling a sphere's volume isn't a contradiction at all. It's a reminder that infinity plays by its own rules. Most things we touch keep their size when you move them, like a marble that stays a marble. But the pieces we're about to meet don't play by those rules. They're anything but ordinary. Mathematicians call these strange fragments non-measurable sets. In plain terms, they're collections that refuse to be measured like regular volume. Because they're non-measurable, you can't assign them a sensible size. It's as if you tried to weigh a puff of smoke. There's no definite number to grab. So when we double the volume of a sphere, we aren't breaking any rule. Those pieces simply don't have a volume to begin with. The paradox disappears once you accept the lack of measurement. Physicists quickly point out, you can't build a machine that actually clones a solid ball. The theorem lives in a realm where physical constraints don't apply. In the end, the Banach Tarski paradox is a pure thought experiment, a dazzling trick of abstract mathematics. It reminds us how far imagination can stretch when we let logic run wild. When the Banach Tarski theorem first appeared, the mathematical community erupted into a midnight-fueled debate. Scholars crowded around flickering candles, arguing whether a sphere could truly be doubled. A handful of thinkers warned that the result threatened the very fabric of reality. If a ball can become two, what does that mean for the world we experience? Most mathematicians, however, treated the paradox as a pure logical curiosity, a whimsical puzzle that lives safely inside abstract thought. Later research showed the same duplication trick works in higher dimensions, proving the phenomenon isn't confined to ordinary three-dimensional balls. In fact, you can split a ball and reassemble the pieces into both a ball and a donut. Geometry pulling off the impossible. The hidden engine behind every one of these marvels is the same silent partner, the axiom of choice, letting us pick points from infinite collections without a concrete rule. You might wonder if this paradox will change how you brew your coffee or walk your dog. In reality, it stays safely inside the realm of pure thought, not your kitchen counter. Still, it nudges us to reconsider what possible really means. Sorry, no secret lab will let you clone a marble with a laser. Physics still holds the line. Mass and energy can't just pop out of thin air. The theorem lives in math, not in your toolbox. What does it do for our heads? It flips the switch on how we picture the infinite, turning a vague concept into a playground of wild possibilities. Suddenly, infinity feels less like a void and more like a toolbox. Our gut feelings love tidy, solid objects. But the Banach Tarski trick shows that intuition can be a mischievous liar when infinity joins the party. Trusting only what feels right can lead you straight into paradoxical traps. Mathematicians get a real buzz from these brain twisters. It's like solving a Rubik's Cube made of pure logic. The paradox is a favorite party trick that keeps the community buzzing with wonder. And here's the kicker. Drop the axiom of choice, and the whole duplication vanishes like smoke. The paradox becomes a litmus test for the foundations of mathematics, showing just how much we rely on that single, sneaky assumption. Imagine space as a rubber sheet you can stretch and fold. The Banach Tarski paradox hints that, deep down, geometry might be more bendable than our everyday intuition suggests. If we set the axiom of choice aside, the magical duplication disappears. The paradox collapses, and the sphere stays just one sphere, no extra copies popping out of thin air. Choosing to reject that axiom is like locking the box. Volume stays safe and predictable. No sneaky, non-measurable pieces can slip through the cracks. But the axiom of choice isn't just a party trick. It underpins countless other theorems. Toss it out, and many familiar results would crumble alongside the paradox. So the Banach Tarski story becomes a window into the foundations of mathematics. It lets us peek at how the rules we accept shape the very shape of mathematical reality. It asks a simple yet profound question. How much of mathematics rests on the freedom to choose? The answer decides whether such wild paradoxes belong in our world or stay locked in theory. So, does the real world actually obey these wild, choice-driven rules? That's the big philosophical question the paradox throws at us. It makes us wonder whether nature plays by the same infinite selection game as pure math. Next time you spot a flawless ball, whether it's a marble or a planet, let that perfect curve spark your curiosity. It's the same ordinary shape that hides a mind-bending secret inside math. And remember, in the realm of mathematics, that one sphere can magically become two. It's not a sci-fi gadget, just a beautiful quirk of infinite sets and the axiom of choice. If you enjoyed this story, subscribe to Take Break, turn on notifications, and share it with a friend who loves a good story.